So today we're going to talk about something called the definite integral. So here is the definition of a definite integral. So you have a function f that's defined for some values between a and b, and you divide that interval into subintervals of equal width. So we did this yesterday with our left sums and our right sums, right? We divided the thing up into equal pieces. And these things are the endpoints of these subintervals. There were always there was one more endpoint than interval, so we let the first one be 0. So start counting at 0. And we let these x1 star, x2 star, xn star be things called sample points in the subintervals. Those sample points could be things like left endpoints. They could be right endpoints. They could be midpoints or something else entirely. It doesn't matter where you pick it as long as it's somewhere within the interval. So you have the interval from x0 to x1, and x1 star is the sample point inside of it. The star just means sample point somewhere. We don't specify where. And then this thing called the definite integral of f from a to b is defined as the limit of that sum. So that's that process that we did. I think we did it with right endpoints for 1 over x squared, where we had to like plug it in, do a bunch of algebra, and then use that magic formula about the sum of I squareds and take a limit. And so what this thing means, this is something called a signed area under the curve y equals f of x from x equals a to x equals b. And what the sign part means is that if f of x is below the x-axis, that area counts as a negative area. That's what the whole signed part means. So that's all that's talking about. It's just this thing, the x, don't be freaked out by the xi star, it just means sample points. So, and that's a way of saying it. And that's, I think I mentioned in class yesterday that when we did it with the right endpoints, the left endpoints would give you the same answer. That's what this is saying, is that you can get the same answer no matter how you pick those sample points. And the reason that this integral symbol looks like a stretched out S is because of the fact that it comes from a sum. Does that make sense? It's also the symbol that's on the front cover of your textbook, isn't it? The guy that wrote the text. Yeah, but it's quite similar. Yes?
The end of your text, what counts as negative?
The area counts as negative. So like if the curve, say, does something like this, you know that this area is 2 and this area is 3, then the value of the integral from a to b of that function, saying this was a and that was b, that would be 2 plus negative 3 or negative 1, for example. And you can kind of think that if you think about it in terms of area, this is like as an x times y, this would be an x, and this y would be a negative number, right? So you can kind of think like with the x and y axes in as context, maybe that's okay, but it doesn't. Anyway, so that's my sort of half-assed explanation. Okay. And so here's the theorem that you use. If you have a function that's continuous, or if your function has a finite number of jump discontinuities. Do you guys know what jump discontinuities are? The things where it does stuff like that. Like imagine a step function, something like that. Then the function is integrable, and that integral, or that area under the curve, exists. So as long as, you don't have to be continuous, you just have to have a finite number of jump discontinuities. Infinite discontinuities are a little bit different. Those aren't like things like asymptotes, vertical asymptotes. Those are different. You'll deal with those in Calc 2 if you take Calc 2. So just tell me what this limit is as an integral. So back on the top of the page, I have written down the integral from a to b, f of x dx is limit n goes to infinity, sum I equals 1 to n f of x sub I star delta x. So in this thing, unlike the ones we did yesterday, this one tells us what our interval is, doesn't it? And it doesn't do anything with the sample points that have been plugged in. So this will just equal the integral from 0 to 1, and the function is 2x squared minus 5x dx. That's it. And so what this integral will tell you is it'll tell you the signed area under y equals 2x squared minus 5x from x equals 0 to x equals 1. That's what it's going to mean. Kind of like a derivative meant a rate of change, right, or a slope of a tangent line. This means area under curve with the whole signed thing thrown in.
Why is the I starred?
The I is starred because it's a sample. It's a general sample point as opposed to being a left endpoint or a right endpoint or a midpoint. It could be any of them. So the star just means random sample point. That's the notation for sample. Yep, that's the notation to say it's some random sample point. And you don't have to pick left, right, or middle. You could just pick something like at the 1/4 mark. It's just somewhere in the interval.
What do we call signed area instead of just area?
Because area by itself means positive.
Oh,
Does that make sense? Like by definition, an area is positive. That's why they say signed.
because it could be negative.
Because it could be negative. If the function goes below the x-axis, the area is considered to be negative. Okay, so this one will equal, what are the numbers on the top and bottom of the integral? 1 and 4. Those are called the bounds. And the function inside is, and this little delta x becomes the dx. That kind of represents how fast x is changing. You do have to include that with your integral. It does actually mean something. And when you get to calculus 3, if you take that class, you'll have dx, dy, and dz, and the order in which they're listed matters. So you have to be not lazy about notation.
So if I get the 4 and the 1 reversed,
That actually also matters. So, and we'll have a little bit of blurb about that in a little bit of time. So, yeah. Okay. So what I really want you to understand from this lesson is that what an integral means is a signed area under a curve. So we're going to find these integrals by interpreting them in terms of areas, which means that these are functions you should be able to graph and then figure out what the area is because they're shapes you're familiar with, like they're triangles or circles or rectangles and triangles put together. So can you graph the function f of x equals x minus 1? What does that look like? Down 1, and then rise 1, run 1. It's a line, right? Okay. You care about the part between the x-axis and x equals 0, which is right here, and x equals 3, which is over there. So the value of that integral is those two areas added together, with the first one actually being a negative number.
Do you just assume that it stops at the x-axis?
The fact that this says 0, yes, you do assume that it always stops at the x-axis, or your areas would always be infinite, right? Yeah. So it's between the curve and the x-axis. So what is the area of that first little triangle?
half.
A half, so we're going to have negative a half plus, what's the area of this triangle?
2.
Yeah, I think I made my box go too far, didn't I?
Yeah.
Yeah, sorry about that.
I'm thinking the area of the square is 4 and half of that is 2.
Yep, exactly. It is specifically half a square, so plus 2, so that's going to be 1.5 or 3 halves. Another way to think about that is you could also see that there's some symmetry. This one and that one kind of cancel each other out. Do you see what I'm saying? Because one's negative, one's positive, right? And so the actual area you're looking for is just this bit, which is 1 whole square and half a square. Okay, anyway.
Negative infinity doesn't cancel positive infinity.
But they're finite numbers. Negative 1/2 cancels positive 1/2. They're not infinities.
Oh, I think you said infinity.
Oh, no.
The other part.
Okay, what does the absolute value of x minus 2 look like? And so V shifted left or right? Right 2. And what are the slopes of the line on that V? 1 and -1. And I will give you grids to graph with because drawing things evenly spaced is so hard. That wasn't sarcasm, I think it's hard. So what is the left part that you consider? How far back do you go?
To
Uh-huh.
-2.
X equals -2 over 2. On the other side, x equals, which I believe is right there. So we're looking at that area plus that area.
How do you know it's not the, inside the box?
How do you know it's not inside the box? What box?
You know, how do you know it wasn't the other area? It was the area underneath and not above the line?
Oh, it's always the area underneath the curve.
Okay.
Yeah. Or above the curve if it's below the x-axis. It's between the curve and the x-axis. Yep. Okay. What's the area of the first triangle?
No, it's,
I think it's 8. It's 1/2 times 4 times 4. Do you agree with that?
yeah.
Because 1/2 base height, right? Maybe Rachel's looking at the next one. Well, I think that's 9 halves. 1/2 and 3 times 3, right? Do you agree? So that's 16 halves plus 9 halves is how many halves? Come on. 25 halves. It's okay, it happens.
Talk about haves and have-nots.
Talk about haves and have-nots, exactly. Okay, so I think that absolute value bars and, lines are pretty easy. Now, you also know areas of circle. Right? There a circle is, you're allowed to use the fact that it's pi r squared, right? Now, the hard thing is almost no one knows what the equation of a circle is when it's written this way. So what is the equation of a circle of radius r? So circle with center at the origin. Radius r. What's that equation? X squared plus y squared equals r squared. Have you seen that before? Okay, take that equation, solve for y. Like if you wanted to graph this in your graphing calculators, you'd have to give it as a function, like a y equals thing. So that'd be y squared equals r squared minus x squared, right? And y equals, I'm going to make a small mistake here, r squared minus x squared. What do I need in front of my square root sign? A positive negative. The positive gives you the top half of the circle. So y equals positive r squared minus x squared is the top half. R equals negative, y equals negative r squared minus x squared is the bottom half of a circle.
Or didn't know that.
Okay? So look at this thing. Do you see how that's a lot like this? So technically y equals root 16 minus x squared. You could think about it as y squared equals 16 minus x squared, or x squared plus y squared equals 16, right? Except for this is only the top half of a circle with r equal to 4. Okay. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, top half of a circle. So semicircle, right? So when you see a root like that, you should recognize this is a semicircle. Like you're gonna have to know that. And that's gonna be the hardest thing probably from these area things. Now, what do the bounds tell you? In our previous questions, they told us like what the leftmost x where the area began and what the rightmost x where the area ended, right? So do,
To the radius,
so it's from where to x equals 4? Where does the origin, yeah, so it's just finding this area. So that integral that you have is the area of a quarter circle with radius equal to 4. Do you see what I'm saying?
How do you know it was a quarter
Um,
and not the whole half circle?
because if it was the whole half circle, the lower bound would be -4.
Oh, okay.
So those bounds tell you the range of x values that you're looking
Specifically
at.
the
Yep,
x
it's saying
values.
specifically x equals 0 to x equals 4. It tells you your interval. And if it was the whole half of a circle, it'd be -4 to 4. Yeah.
If there was a negative in front of the root, we'd be looking for.
If there was a negative in front of the root, the graph would have been below the x-axis, and then it would have been, your answer would have been a negative half or quarter of a circle depending on the bounds. Yeah.
Say we were working with a circle of the same parameters, but instead of a 4, it was a 3. How would we find the area then?
If it was 3 minus x squared,
No, if it were,
oh, if it were 0 to 3,
yes,
it won't happen.
they won't give us one of those?
Because you don't know how to find the area of something like that. To do that, you have to know more math than you're going to learn in this course. Okay, so yeah, to do that, you'll have to know some calculus 2 stuff, which is technically called the trig substitution, and you're not going to learn it in this class.
already gives us the radius for that.
This will give you, it'll be really easy geometric objects you know how to work with. So the area for this thing will be 1/4 pi r squared, or 1/4 pi times 16, or 4 pi. So the value of that is 4 pi. But you won't go from like 0 to 3 because you don't know how to find the area of a truncated circle like that. And to do so, it's actually quite complicated. Okay, part B, if you look at part B, what's the thing that messes you up? The 2. So you can do this 2 ways, okay? Way 1 is you can graph this picture, the root 9 minus x squared. What does that look like? It's not like what we just did, right? It's a semicircle. R equals 3. What does doing plus 2 to it do then? Moves it up 2. So here's your semicircle of radius 3.
I wanted to say circle, just
Okay. And it moves it just straight up 2. So that puts it up 1, 2, 1, 2, 1, 2. And you have a semicircle on top of a rectangle.
Does the rectangle matter?
It does, because now to find the area under the curve, you find the area of the rectangle plus the area of the semicircle.
Oh, so it's included.
It's included, yeah. So even though the function doesn't go like all the way, like the graph of that function really is this, and it doesn't extend down to the x-axis, but the area underneath it
That's the plus.
includes the rectangle as well, because it's the area underneath that curve down to the x-axis. Does it make sense why I shaded the whole thing?
Yeah.
Because that goes -3 to 3 this time? Okay. So this will be, what is the area of that rectangle? 2 by 6, okay. So 12 plus 1/2 pi times 3 squared. So 12 plus 9 pi over 2, I believe. Here's method 2.
Do you want us to come?
No, I don't care. You can actually do it like this. And you can think about it as 2 separate curves. What would y equals 2 look like? Because that's what that first one is. It'd be a horizontal line shifted up how much? 2. And it would go from -3 to 3, which gives you that thing being 12, right? And this next one would just be an unshifted semicircle of radius 3, and that gets you the 9/2 pi. And then 12 plus the 9/2 pi gives you back what you had. So it's kind of like you can break derivatives and limits up into individual pieces. You can do the same thing with these integral things.
Is that because they're gonna get complicated?
There might be some, I think that there might be a homework question that's like x plus the root, which is a little bit harder to visualize than like 2 plus the root. So you have to think about breaking it into two pieces. Okay. All right, so find each integral by interpreting it in terms of area. So the area from 2 to 5. So that'd be from here to, I think, right there. Do you guys agree? And I think about that as rectangle plus triangle. So what's the area of the rectangle? Plus 1/2, base is 2, height is 3. So what's that? The value of the integral from 2 to 5 of f of x dx?
6?
6, yep. Does that make sense? Okay. How about 5 and 9? So that's from here to there, right? There are probably lots of ways to look at it, but I think about it as this triangle, and a square. That's just my personal preference. Okay, so the first one will be negative because of below the x-axis thing. 1/2, base is 2, height is 3. Do you agree?
You also just include this 1/2 plus the height is -3.
Yeah, something like that. You can include it as 1/2, make the height -3. It doesn't matter either way. As long as the result is negative, you're fine. And then we're going to have -4 for the square, right? And minus how much for the purple triangle? -1/2. I think 1 times 2. Do you agree? So that will be -3 minus 4 minus 1, or -8.
So that's why it was the sign thing before, because we're having negative areas.
Exactly, that's what I was
It's
saying,
kind of
sign
weird.
thing, which is kind of weird, but they might have physical interpretation. So like if this was feet per second and this was feet, this tells you the distance that you go forwards, and the negative part tells you the distance that you go backwards. So that's one reason that this negativity in the area actually matters. And that would be something that would tell you your displacement. If you want to know distance traveled, you'd have to add together the areas as if they were both positive.
So what about with this particular question where it's not asking about signed areas? It just says
When the integrals by definition mean signed areas. Like that's what it means to have that integral symbol.
I'm
And if
sorry.
it doesn't want signed areas, it would ask for it in a different way.
Y is feet and x is feet per second instead of just seconds?
Well, is possible, right? And I probably mix those up. This really could have been, usually this would be feet per second, and this would be seconds, we'll say.
Yeah.
There we go, then that makes it feet. Okay, thanks. All right, 3 to 7. So right here to right there.
Zilch.
Yeah, do you guys agree with his quick analysis that that's 0? This is obviously the exact same triangle as that, right? One's above, one's below. Oh, bam, they cancel.
So that's like the forward back to start.
Victory dance, yep, exactly. Okay,
More like that.
okay, so now we're gonna do the same thing as yesterday, except for yesterday, I'm pretty sure in your homework, all of the things that you found left and right sums for were always positive. I don't think they went into the negative area thing at all. So x squared minus 2x on the interval from 0 to 4, n equals 8, using a left Riemann sum. So this left Riemann is just the name of the guy who came up with this, like it was his idea. But left sum with 8 pieces. So first of all, let's graph x squared minus 2x. If you're graphing functions, a really, really good place to start is to find the intercepts. Does that make sense? So can you find the x-intercepts for this guy? Set the y to 0, x squared minus 2x. Take out an x, and you get x minus 2. So where does that graph cross the x-axis? 0 and 2. And I'm pretty sure when you input 1, you get -1. You input 3, you get, I don't know, something up there. But it does give you the gist of what the picture looks like. You know it's a happy parabola, so it looks about like that. Okay. So what is the delta x in this case? If you have interval from 0 to 4 and 8 pieces, how wide will each of your subintervals be? A half, yep. 4 minus 0 over 8, or a half. So personally, I just look at and visualize my interval. I start at 0, I end at 4. First I have 0.5, then I have 1, right? Then I have 1.5, 2, 2.5, 3, 3.5, and 4, right? Those are like the points that I'll be plugging into my function. So if we do the left sum, what is the common width of every single rectangle? 1/2 or 0.5, either way. And then how do you find the heights? What do you do? You find the y's, and how do you find the y's? What do you do with the numbers? Plug them into the function, right? And if you're doing the left sum, you plug in 0, 0.51, 1.52, 2.53, 3.5, but not 4, right? So just tell me what you're doing. Say f of 0 plus f of 0.5, and then do this, okay, plus dot, 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 and tell me where you end. Does that make sense? Like that can be showing enough work that I get that you understand what's going on. And then when you plug those numbers in and work it out, you end up with 3.5. On your homework, you'll actually have to do the calculation and plug those things in. And it does get, the reason I choose to assign problems that use n equals 6 is 14 seems too small and 8 seems too big. It's quite tedious to button punch, isn't it? Yeah. So on a quiz or a test, I might just ask you to give me this expression and not actually work out what it is.
They call that expression, yes.
Yeah, give me something that will give you the sum. Okay, how about this one? So if you're doing the right sum, what's going to change? Will the fact that there's that 0.5 or 1.5 out in front change? No, but what will your starting point change? Start with 0.5, and then you'll plug in 1. What will be the last thing you plug in?
3?
4. The last thing you plug in is 4.
Okay, about 3.5 was the end.
3.5 was the end for the left sum.
You shift over 1.
Yeah, you shift it over 1, because you think about all those little intervals, you use the left endpoints for the first thing, and then use the right ones for the second thing. And the first endpoint is not a right endpoint, it's a left endpoint.
Actually, additions to that.
And this is 7.5. I hate example 6. I have 1 because it's my duty, okay, but we'll do 1 and we'll be done. So find that area exactly. So to find it exactly, we have to do that thing we did yesterday, which was find the limit and ugh. So f of x is x squared minus 2x. Okay, so you have that curve. If you do n chunks, delta x will be 4 minus 0 over n, or 4 over n. So looking at our little interval, we have 0, 4 over n. What's going to come next? 8 over n, and then 12 over n, right? Up until you get to 4, which is 4n over n.
That always kind of freaks me out.
It freaks me out too, okay? So like, don't worry about it. So then the right sum, what is the common width of every single interval?
4 over n.
4 over n. And then you plug those things into the function, right? So we're going to have f of 4 over n plus f of 8 over n up to f of 4n over n. Does that make sense? I'm just not writing down what they are when I plug them in because like it's easier to write f of than to write x 4 over n squared minus 2 times 4 over n. Okay, that's 4 over n times, so sigma symbol, I equals 1 to n, f of, so which part of that expression, the stuff inside the f, is changing? The numerator or denominator? Numerator. Denominator is still n, and the numerator, this is 4 times 1, this is 4 times 2, right? So this you say 4i. Because first you've plugged in 1, then you plugged in 2. The I is the thing that's going up. Okay, and now what we're going to do with that is plug it into the function. So 4 over n sum I equals 1 to n, and that becomes 4i over n, the quantity squared, minus 2 times 4i over n. That's just using what f of whatever means. Just plug the number into the function, right? Okay, now I'm going to do some algebra. So 4 over n, sum I equals 1 to n, 16i squared over n squared minus 8i over n. Is everyone okay with happening with that stuff? Is everyone okay with what happened from between those two steps?
Yeah.
It's not very hard, right? Just squared the, okay. Now here's what I'm going to do next. I'm going to write 4 over n, big parenthesis. I'm going to sum the first thing, and then I'm going to do a separate sum. I'm sorry, I meant to put a minus sign there. Take away the sum of the second thing. And let's think about why that's okay. So how it's written in the second to last step up there is you have the I squareds plus the single i's. And you do I squared plus I squared plus I squared plus I. This one just does all the I squareds first, and then does all the i's separately. It rearranges the way that things are ordered. You can rearrange things when you're adding, right? That's what it does. Okay. Oh, and I made a mistake. That should be n squared. Oh, God. Okay, and we're 90% there. So now the next thing you can do, oops, missed my things, is you can take out the 16 over n squared from the sum. And the reason is that that's going to be a greatest common factor. When you plug in your i's, you're going to have 16 over n squared times 1 squared, plus 16 over n squared times 2 squared. So I is the thing that's changing in that stuff. The things that are just constants, obviously the 16 can come out as a GCF, and the n squared actually also is a constant because it's a fixed endpoint. It's a number you choose, and then it's always the same. And now, in your book, on page 381, there are formulas for what this and what this adds up to. So that first one is doing like 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. This next one does 1 plus 2 plus 3 plus 4 plus 5 plus 6. It's pretty easy to prove what the second formula is, but I don't think I have time to show you today. So this is using the magic on that page. Okay, the I squareds add up to n plus 1, 2n plus 1 over 6. And the i's add to n times n plus 1 over 2. Yeah.
Where'd you get that n plus, n times n plus 1?
This equals this, and this equals that. As in, you're not supposed to understand why.
Oh.
Okay, like they are formulas that tell you how to add those things up. Instead of actually having to add up, say, numbers 1 through 100, you can just plug 100 into the formula.
Okay, so those formulas were just like.
If I gave them, if you're in your homework, you would look them up and you would use them. Like I have the second one memorized. I can derive that one, but the first one, I don't even know how they came up with it. Like it's just hard. So now this is an expression that tells you the area no matter what n is. Like n could be 100, 1,000, a million, a billion. To find the area exactly, n is the number of pieces you've taken, right? So the area exactly will be the limit as n goes to infinity of that thing. And before we do that limit, how about we simplify just a teensy bit? So you got 4 over n. Can anything in that first term cancel? What I mean, like, can anything cancel? The 16 and the 6 can cancel a little bit, right? That can become 8 over 3. How about any of the variables?
No.
And n can cancel, right? So that'll be n plus 1, 2n plus 1 in the numerator, and the denominator will just be a single n now, right? How about in the second one? Can anything cancel?
The 8 and the 2,
So it'd be 4, and how about anything else?
the ends.
Yep, so 4, is that just n plus 1, is that all? I think that's it. Limit n goes to infinity. Okay, that becomes 32 times 2n squared plus n plus 2n plus 1 minus 16 times n plus 1 all over 3n squared. Oh, shoot. First one over 3n squared. Second one over n. Okay, how did I get that? What did I do? Distribute the 4 over n. And now I swear we're almost done. With this first limit, who are the important components that actually matter when you find it? Look at the powers in the top and the bottom. They're the highest power is they're the same, right? So where's that limit going to go? Let me write it one more time. Let me say limit n goes to infinity. If I say 64n squared plus 396n plus 32 over 3n squared. Use what you know from like algebra 2 or pre-calculus. If the ratios in the top and bottom match, where's that going to go? 64 thirds. Okay. How about the next one? Minus the limit n goes to infinity, 16n plus 1 over n, or plus 16. Where's that going to go? Minus 16. And so this equals 16 thirds. Okay, Okay, made you suffer once. You remember how finding derivatives was super difficult, like with the limit definition where you had to do f of x plus h minus f of x all over h, and then there was an easier way, and there were these rules that were a consequence of that? This is the only one we're gonna do this way. There isn't even one in your homework, because it's so damn tedious, I can't justify making you do it. The point is, if you limit a sum, you get an integral. That's what it makes. And this estimation technique is an important idea. And the idea that if you want to estimate something, you break it into little chunks, and then you limit the number of chunks to infinity. That comes up repeatedly. The details of, like, the purple steps really aren't important to memorize, okay? Point is pain in the ass, okay? That's the point. Now moving on. So we briefly discussed yesterday that you could estimate the area under a curve using middle points, right? So this is a really, really great approximation tool. So if you have your curve from A to B, step one is to divide into n chunks. Delta x equals b minus a over n. And then find the middle points of your subintervals. And plug into your function. And so how I would draw that picture is I'd say, okay, here's my middle point. I go up to the curve there, and I find the height. Middle point, up to the curve, I find my height. Do the endpoints of those intervals get used explicitly? Do you know what I mean by that? Do the endpoints of those subintervals get plugged into your function when you're doing the midpoint rule? No. But they allow you to find the middle points, right? So the endpoints of the subintervals are used to find the middle points, and then the middle point is what gets input into the function. Is the width of the subinterval different than it would be for the left or right sum? No. Okay. So we're going to use that to approximate some functions. So approximate the function 1 over x on the interval from 1 to 2. So first of all, 1 over x, if you're looking in the positive first quadrant, looks something like that-ish, right? Approximately. And we care about it from 1 to 2. So if you're using 5 subintervals, how wide should each subinterval be? 0.2, yep, it would be 2 minus 1 over 5, 1/5, or 0.2. So I'm going to draw that sort of like x-axis up here. I have 1, 1.2, 1.4, 1.6, 1.8, and 2.0, right? One, 2, 3, 4, 5. So what is that first middle point that actually gets plugged in? 1.1, yep. So this one, remember left sum we used L sub, R sum we used right R sub. For midpoint rule you say M sub 5. So how wide is every single box? 0.2, right? Because from there to there is 0.2, right? So 0.2. And the first number that gets plugged in is 1.1. What does it get plugged into? 1 over. So it gets 1 over 1.1. What's next? 1 over. 1 over 1.5, right? 1 over 1.7, and then 1 over 1.9, 9, right? So you take your intervals and plug in all those middle points. And then if you use calculator, it's approximately 0.692. Does anybody have a calculator in their hands right now? Tell me what natural log of 2 is equal to, approximately.
0.693.
Okay, so this, because I know a bit more math than you guys do at this moment in time, this is the actual area. This is the estimate. I think it's kind of amazing. You can take 5 chunks and look at how close you are. So, it's kind of cool. Okay, so
Especially we were in the good part of the curve too, then, huh?
it was probably because the curve kind of flattens out so much that it worked out so well. But the midpoint rule is accurate with very, very few subintervals. Like, it doesn't take much. I mean, it depends on the curve, but it's more, way more accurate than left and right sums. Okay, midpoint rule with n equals 6 to estimate secant of integral secant x over 3. So on the interval from 0 to pi. So I'm not going to attempt to draw that picture because, like, I don't know, I mean, it's just not going to be very pretty. Just all that matters is what things you plug into that function. So interval goes from 0 to pi. If n is 6, what's delta x? How wide is each subinterval? Pi over 6. Yep. So you've got pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6. I know some of those reduce, but like it's easier to think about them not reduced, at least for now. So if you were doing the left sum, what numbers get plugged into your function? For the right sum, you'd plug in pi 6 through pi, right? How about for the middle points? What's halfway to pi 6? Pi over 12, yep. And this will be pi over 12 plus pi 6. Pi 6 is 2 pi over 12, right? So that will be 3 pi over 12. What's going to come next? 7 pi over 12. 9 pi over 12. I know it reduces, but you know it's easier to see the pattern without reducing. And then 11 pi over 12.
Makes sense for evenly spaced.
Well, I mean, yeah, they're pretty much always going to be evenly spaced, except for that one example in your homework. Okay, what's the width of every single interval? Pi over 6. And then I want to show you one thing with arithmetic. If I do pi over 12 over 3, that's the arithmetic that's happening inside the secant function, right? A lot of you struggle with figuring out what this is equal to. You know, if I say division by a fraction is multiplication by the fill in the blank reciprocal, what is the reciprocal of 3? 1 over 3. So that's pi over 12 times 1 over 3. So pi over 36. So that'd be secant of pi over 36. The next one's going to be secant of 3 pi. Will the over 36 change? No, so it'll be over 36 again. Plus secant of 5 pi over 36 plus secant of 7 pi over 36, secant of 9 pi over 36, and then, is that it? No, secant of 11 pi over 36. You could, of course, reduce the ones that reduce, and to plug in a calculator, you have to have you probably got to use secant as 1 over cosine, because most calculators lack a secant button. Also, make sure you're in radians. Okay, so just a couple things to watch out for. You should get about 3.938. And I cannot quite as easily as the previous one compute the actual area there. I can't do that in my head. If I give you a quiz that requires any funkiness like this, I will definitely give you, you will get to use a calculator. So bring one if you have one. But I think that what I did was I just kept the numbers pretty easy on the quiz, and on the homework, you'll have to use a calculator. Okay. All right, so here's some properties of the integral, and these are actually not very hard. So the first thing is that we had a question about, does the order of the A and B matter if I flip-flop the 4 and the 1? Is that going to affect stuff? And the answer is actually yes. So you assume that A is less than or equal to B when you do these integrals. It's always assumed that that is the case. So if you find the area under the curve from A to B, it's the same thing as negating the integral and flipping the bounds. And here's the reason why. For the first case, delta x is b minus a over n. And if a is less than or equal to b, this is a positive number. But for this one, if your integral says, instead of a to b, it says b to a, then delta x is a minus b over n. Notice that these are opposites. So it's kind of like in the second one, you're going to have this negative width or something like that to your integrals. But the point is, flip-flopping the bounds negates the integral. So that one makes less intuitive sense to me, but the next one makes a lot of sense. If you integrate from one number to another number, that's the same number. So think about that as a picture. It's the area under a curve at a specific point only, right? I'm pretty sure that in geometry they said that lines have no area, right? So that's why this is 0. Lines have no area.
Yeah, I see what you're saying.
So I mean, I can't draw something with no area because it would be invisible, but lines have no area. This one seems like it's sort of tricky, but it's actually quite easy to understand if you look at a picture. So C is the function y equals c, right? It's a horizontal line. So we'll assume it's positive, but if it was negative, it'd be drawn below the x-axis, right? So A and B. So suppose A is there and B is there, right? Every single time that's going to make a rectangle, isn't it? What is the height of the rectangle? C, right? What is the distance from this end to that end? B minus A. And that would work even if C was negative, right? Because if C was negative, you'd just take negative C times B minus A.
We'll just be on the other side.
Just be drawn down below. And also would work if A was over here, like A was some negative number, because then say if B was 4 and A was negative 3, 4 minus negative 3 makes 7, which is how far it is from negative 3 to 4, right? Okay. And then the last two properties are a lot like the properties for derivatives. So with derivatives, what happened to constants? They could do what? They could pull out. So the constant pulled out. And we also kind of talked about this one earlier, that you've got two things added or subtracted. Remember we had that one problem we did two ways, where we first did the picture, shifted up, and we also could do two pictures? That's what this says, is you can break the integral up into two pieces and find the area under first curve plus area under second curve. And I'm pretty sure that there's a homework problem where it's like integral 0 to, 5, x plus the root of x of 25 minus x squared dx. And you're like, oh my gosh, it's a line in a semicircle, right? But I can't graph that. So what I would do is break it up into 0 to 5x dx plus 0 to 5 root. And then this first one's going to be a line. This is especially a quarter circle, but you can do each piece separately, is the point.
Maybe I'm just not seeing it, but why can't you graph that?
Oh, I can't graph this thing with the x because adding x isn't an easy shift. I mean, you can graph it, I just can't do it in my head. I have to really think of what it would look like. The one that we did was like 2 plus the root of 25 minus x squared.
I get what you mean, I guess I'm seeing the increase as.
But then what the curvature does, it would be less obvious to me that it would be a line in a semicircle, but maybe it,
You're right.
yeah, it'd be strange to draw is my thought. So I think it'd be easier to,
Computer programming to do it.
of course, yeah, but without a computer program, I think it, and I would be less confident in my skills to draw that, so. It might even end up that the circle ends up being sort of curved, but I really can't visualize it. Okay, because what it might do is it might create like this line, and then it might like turn the semicircle on top of it or something like that. I don't know. And I think it'll kind of like shift it a little bit, and it'll still have the same area as a semicircle, but be shifted some. I make no commitments what the picture looks like because I'm not sure. Okay. So we're going to use those properties to evaluate some integrals. Now, much like with derivatives, does the fact that the variable is a different letter really matter? Not really, no. So if the integral from 0 to 1 of x squared is a third, we proved that, right? What's the integral from 1 to 0 of t squared? So what's the thing that changed, other than the t and the x? First one's 0 to 1, right? Second one is 1 to 0. So if I negate this, I can change that to 0 to 1. And now can you say what it's equal to? Negative a third.
Do you have to change it? Yeah, you do.
You do. Just to show that, okay, well, I know that integral from 1 to 0 equals negative integral 0 to 1. Or you could just recognize that, okay, well, the bound's flipped, so it's the negative of that answer. That's okay, too. Okay, this one you kind of break into pieces. So the first step is that you break it into integral from 0 to 1 of 4 plus integral 0 to 1 3x squared. And then you attack each piece separately. So visualize what that first one looks like. The graph is y equals 4, which is up how much? 4. And you care about it from x equals 0 to x equals 1. So it's a rectangle, and its base is 1, its height is 4. So the area is 4. With that next piece, the 3, the constant, can come out of the integral. And now, do you know the value of that thing? We proved it earlier, didn't we? The integral from 0 to 1 of x squared dx is equal to 1/3. So that will be 4 plus 3 times a third, which I think just gives us 5 in the end. Right? Okay.
If they didn't tell us what x squared was equal to.
If they didn't tell you what the value of that integral is equal to at this point in time, you wouldn't know a way to do that because a parabola is not a standard geometric shape that you know the area underneath it. Yep, but we will learn another way after we finish this lesson to figure out these. We're going to learn the shortcut. Okay, this is something I didn't actually put in a property, but it's a pretty easy property to visualize. So you have some curve, f of x, and the area from 0 to 10 is 17. So I don't know what happens. The curve does something, maybe, not sure, but from 0 to 10, the area is 17. Okay, so somehow, maybe there's negatives cancel, maybe it's all positive, but somehow it's 17. So you know the area from 0 to 8 is 12, right? So here's the area from 0 to 8. The area from 0 to 10 is all of that, right? So how would you find the area from 8 to 10 using the information that you've been given? As in, I want you to get me this part. 17 minus 12. Do you guys agree with that? Then I could take the area from 0 to 10 and take away the area from 0 to 8. or 17 minus 12 gives you 5. They've got to tell you what those things are equal to, but the point is that this area is additive. You can find the area from 0 to 8 plus the area from 8 to 10, and that gives you the area from 0 to 10. And the picture is totally obvious, right? You can totally visualize that. Okay. And example 11 on the next page has no space because none is needed. Who cares what the curve is? What's the integral from 3 to 3 of any curve? Nothing, just 0. So there are a fair amount of homework problems in WebAssign, but they're like this, right? See what I'm saying? It's like easy properties that will not take long. There's none of the tedious stuff there.
That's, I guess, an important concept.
It's an important concept to know kind of that this is the definition, but I'm not going to make you do that definition.
You should put a couple of those on the test.
It'd take forever and be awfully great. I don't want to do it to myself. I'm not that masochistic. Okay, so here are just some comparison properties, and these are pretty intuitive as well. If your function is positive for all the x's in your interval, then the area under the curve is going to be positive. Does that make sense? Okay. If you have one function who's bigger than the other function the whole time, so you have your f of x, below it you have your g of x, then the area under f of x is bigger than the area under g of x. You buy that? Okay. Now the last one is a little bit less intuitive but not super awful. If your function f of x is what's called bounded, so there's a number that it's never lower than and a number that's never higher than, then the area is in between these two boxes. And the easiest way to prove that is to look at a picture of something where just the function's positive for simplicity. So suppose here's your function y equals f of x. It's okay, you can open your Swedish fish. And here's your a, and say there is your b. This number is what they're calling like their lowest number. This number over here is their highest number. Okay. Now here is the actual area under the curve, right? Now what this inequality says is that that area has to be bigger than that box. Do you buy that? That box is this area, right? And smaller than the box where you take the height to be the highest point, and that's that area. So it's just saying if you can find the lowest point and the highest point, that'll give you two boxes that bound the area between them.
Makes sense.
Yeah, it's not super hard. That's the last thing we're going to do in this lesson is use that to estimate some things, like just estimate some areas, looking at the lowest and highest points.
Is that to give like the middle function?
Just to give a guesstimate as to where it is. So for example, x to the fourth. So on the interval from 0 to 1, what is its lowest point? 0. What is its highest point? 1. So the min 0, max 1. So the actual area is bigger than 0 times 1 minus 0, or 0, and that would be the box of height 0. It's less than what number? 1 minus 0, or 1. So that's the lower box. That's the higher box. Somewhere in between 0 and 1. Okay, oh, chapter 4 is going to come back. how would you find, this one's a little bit more tricky. How would you find the min slash max of y equals x e to the negative x on the interval from 0 to 2? How do you find mins and maxes? What do you use? The derivative. Y prime would be 1 e to the negative x plus x e to the negative x times negative 1, right? Set it equal to 0. E to the negative x, 1 minus x. When is that equal to 0? At x equals 1. And then you'd find y of 0, y of 1, and y of 2. Right, because it's the closed interval, right? You find the highest, absolute max, absolute min. Pretty sure y of 0 gives us 0, right? What does y of 1 give us? What does y of 2 give you? Yeah, 2 over e to the 2. And maybe the minimum is totally obvious, right? This one is obviously the minimum, right? Isn't e awfully close to, say, I don't know, 3, 2.7? So you've kind of got 1/3 versus 2/9. Who's bigger? 1/3. So this is the max. So the lowest this thing could be would be 0 times 2 minus 0, or 0, because 0 is that little lower m value. The highest would be 1 over e times 2 minus 0, or 2 over e. That's it.